All right, so welcome everyone to GADEPS. So today we are very happy to have Ananyo Dan, who will talk about topological and geometric obstructions.
Yeah, thanks to the organizers for giving me this opportunity. So I think I cannot see any of you guys right now. So if you have any questions, just open the mic and you can ask. So uh, that will be best. Okay, so I start. So there are a lot of experts in this topic. So I will say a few things before I get into the technical details. So what I am trying to do? So we all know that there is a geometric obstruction theory, by which we mean that if I start with a smooth projective variety and I look at a local complete intersection subvariety in here, then we always want to know if I take a infinitesimal deformation of the smooth projective variety or a first order infinitesimal deformation of the smooth projective variety, whether this smaller subvariety, which in this slide is denoted by Z, whether this Z also deforms in this when I deform X. Now, this question, the obstruction to this question, I will call geometric obstruction. And there is another question that we can ask is that we have, since we have a smooth projective variety, the fundamental class of Z of this local complete intersection subvariety will, the cohomology class of this will be a Hodge class in the correct codimension. For example, if the codimension of Z is P, it will be a PP cohomology class. If you are not familiar with this notation, I will get back to the notation in the next slide, so not to worry. So just there is a notion of the Hodge class. So this is, now you can similarly ask whether when you have an infinitesimal deformation of X, whether this cohomology class or this Hodge class deforms as a Hodge class. Okay.
Sorry, I
Yeah.
can't see the mouse that you are moving in your screen. Maybe.
I'm not really moving any mouse. I am just talking.
Okay, okay, okay.
Sorry, I am. Yeah, but if you have any, if you're not able to understand, just don't feel shy. Um, so what I am trying to I am trying to compare the geometric obstruction of this deforming Z to the topological, so which I will call the topological obstruction, the obstruction to deforming the cohomology class of Z. So now I move the mouse. So I have written these two questions. One side is this geometric question, which I just said that whether the local complete intersection subvariety Z in here deforms to a local complete intersection subvariety XT when I take a infinitesimal deformation. So here I have taken a first order infinitesimal deformation, but you can replace it by any local Artinian ring, which will mean that you can look at any infinitesimal deformation. And so this is the geometric side, and you have somewhat of a topological side, which is whether the cohomology class of Z deforms as a Hodge class. So in the topological side, you have the relative Deram cohomology, and the deformation of the Hodge class is something. So in this case, one can check. It's not obvious, but you can check that this Deram cohomology class of this xt over spec ct is simply a tensor product over ct mod t square of the cohomology of xz of just x of the special fiber with this dual ring. So it's just cohomology of X tensored with dual ring. Similarly, if you had a Artinian ring instead of this dual ring, you can also write it as the tensor product of the cohomology of X with the tensor product with the local Artinian ring. So that is a result that this Deram cohomology looks like that in this specific case of local Artinian rings. And this question, whether the Hodge class in X lifts to a Hodge class in this relative setting, in this setting, is asking that whether the cohomology class of Z deforms as Z tensor 1. I mean, it looks like you can always do that, but that is not always true. And there are the natural obstruction theories to this, which comes from Hajj theory. On the topological side, it comes from Hajj theory. And on the geometric side, it comes from deformation theory. So I will try to compare the two things. So the goal, so these two questions are, the experts are already familiar with these questions and they have studied these questions. And there is already quite a bit of theory on how to compare these two things. One of the tools is the semi-regularity map. Now, the point is that the semi-regularity map is slightly hard. It is a bit hard topic, especially because it is not always very computable. We cannot always compute what is the semi-regularity map and when it is a semi-regular variety. And also this notion of semi-regular varieties, we will see, is a very strong notion. So if you want to really compare the geometric obstruction theory to the topological obstruction theory, the best way to do it is to do it in the local setting. So we will see that the geometric obstruction theory lies in the first cohomology of the normal bundle of this local complete intersection subvariety. And in the topological side, classically it lies in a sheaf cohomology, which is supported on X. So typically it will be supported on X. It's a sheaf cohomology on X. But we will replace this object. We will give a new formulation of this topological obstruction, where we will replace this. For example, in the divisor case, it is always the obstruction lies in H2 of OX. Now we are going to replace this H2 of OX, for example, in the divisor case, by H2, the local cohomology. We are going to now slowly shift to the local cohomology and show that all this obstruction theory is really captured in the local cohomology setting itself. The advantage of doing this is that it is slightly more computable, because some of the computations boils down to computing the local cohomology on points. And also it gives us a slightly better understanding of what is going on, how to go from this geometric obstruction to the cohomological obstruction. So this is mainly heuristic, so I have not given any details. But if anybody has any questions, they can also ask. It's not too soon.
Maybe if you want to,
yeah.
I think I am getting, I'm almost forgetting the thing. So taking mod t square, it will be basically just considering that a kind of tangent space, no?
Yes. Yes, t square is the first order infinitesimal deformation, and it corresponds to taking the tangent space to, in this case, if you have a good moduli space, for example, if you're looking at hypersurfaces, you can look at the Hilbert scheme.
Oh.
So a typical thing will...
Something also, for me, always taking one parameter families is a kind of strange. So did your t is one parameter, this one-dimensional parameter, no?
No, this one is not. So I am not looking at CT. I am looking at very infinitesimal. So I am looking really at the tangent level, as you said. I am not gone to the one parameter family. Because if you want to go to the one parameter family, you have to take CT mod t power n for all n, and then you have to take the limit. So I have not gone till that. I am just looking at the tangent level.
Okay.
Good. Any other questions? Okay, so now it will be a bit boring for the experts, but I just wanted to recall this for if somebody has not seen this. So I start with a smooth projective variety of dimension n, and we have the well-known notion of Hodge decomposition, which tells us that for any integer k, we can write the cohomology, the kth cohomology of the smooth projective variety as a decomposition of this p comma k minus p pieces, and you can identify each p k minus p part with this is kind of a canonical identification with HK with a Schiff cohomology. This is on the right hand side is a Schiff cohomology, on the left hand side is a bit more coming from harmonic analysis. So and what the property that is very useful is that if you interchange the two indices on the top, you get conjugate. So the conjugate, the complex conjugate of P k minus P gives you k minus P P, and the other way around as well. So this is, and what this gives is one of the inferences that you can draw from here is that the dimension of these two objects are the same. There are already quite some important conclusions that you can derive from just this description. So you should be careful that this is only for smooth projective varieties. Now, the Hajj class that I was talking about in the first slide, where the cohomology class of a subvariety lies, is here I have written it for any k, but I can also write it for 2p. So if I write H2p, there will be a piece in the right hand side which is just of the form p comma p. And that is, these are all with complex coefficients. These are all complex vector spaces. Now, so I will always look at rational Hajj classes because the theory gets more complicated if you look at integral Hajj classes. So just for simplicity, I look at the rational Hajj classes. The rational Hajj classes will be the intersection of this complex vector space HPP with the rational cohomology H2P of X, which I will denote by HPP X cube. Now you can, so I will not, so just for any closed subscheme in X, you can get a fundamental class in this PP class in the HPP of X. The way to do it is that you first define it for irreducible subvarieties. The way you define it for irreducible subvarieties is that if Z is irreducible, you first resolve the singularities. You have this thing which I denote by Z tilde, and then you have a push forward map on the homology from the H2n minus 2p. So if the irreducible subvariety is of codimension p, you take the generator. There is exactly one generator in of the homology class H2n minus 2p of the resolution of Z, and you look at the push forward in this H2n minus 2p of X. In some sense, if you look at it in terms of the cohomology, it is what is known as the Gisin map. The image of the generator of this homology is what we call the fundamental class. Later on, we will look at a more explicit description of the fundamental class, which is also known to some of you, but that is necessary to what I explained, to go to the local situation, to the local obstruction. We will use that, but that comes later. So right now, we just look at the fundamental class of a closed subvariety. Now, what you can do with this information is that you first start with a family of smooth projective varieties. Okay. You can, for simplicity, you can take that B is irreducible. And you look at so you can always define this object. This is the right derived functor. So it's a higher direct image of Q. Q is the constant Schiff. So what is important here is that we are now working in the analytic topology. So in this analytic topology, this object still makes sense. So you can look at the higher direct image of these rationals, and what you can observe is that so what is the fiber? So you have this R2P of pi lower star of Q. Now, the fiber at every point is, you can check, is simply H2P, the cohomology H2P of X. So if you take the point small b in B, then if you look at the fiber of this R, what is the value of this H2P restricted to this point, you will get the answer is H, the cohomology, the 2pth cohomology of XB. Now, by Ersman's theorem, we know that if you have a smooth projective family, the cohomology does not change in some sense. So there is a isomorphism between the cohomology groups. That makes this object into a local system. So recall that local system means that in the analytic topology, you can, for every point, you can find a small open neighborhood such that this is like a locally constant sheaf. So this is, the local system is really a locally constant sheaf in the analytic topology. Okay, any questions? Okay, so what we do is that, given this setup, so we have this local system, we have this smooth projective family, so we take a base point. We want to start with a cohomology class. So we want to start with, say, a Hajj class, meaning that I have gamma in HPP of XQ. Okay. Now, I want to kind of extend this to the whole family. I cannot extend it right away to the whole family, but what I can do is that if I look at a contractible open neighborhood of this base point, then, as I said, that this is the local system is a locally constant sheaf. So I can always find a contractible open neighborhood on which this thing is trivial. The restriction of this local system to this open neighborhood is trivial. This means that gamma extends uniquely to a flat section. So if you remove this word flat, you will no longer get unique. But as soon as you, so because flat section is determined by the fibers on a point. So if you introduce this notion, if you restrict to this notion of flatness, this gamma that you have on the HPP of X extends uniquely to a flat section on this whole local system on this small open neighborhood. Now, if somebody, so flat section simply means that, so you have the Gauss-Manin connection on this local system, and flat section simply means that if you apply the Gauss-Manin connection to this section, you get 0. So it's really, there is not much change to this section in some sense. Okay. So now that you can extend, when you can extend kind of uniquely to the whole, to small enough open neighborhood, and you can also do this process on the whole of B. You can cover the whole of B by such contractible open neighborhoods. And so on each of these contractible open neighborhoods, you can define this notion of Hajj locus, which consists of all the points U. So here we had, here we had this gamma, which extends to this flat section of the locally constant sheaf restricted to U. I am looking at that section, this gamma bar, and I'm evaluating at all the points on this contractible open neighborhood. Now we know that, you see, this local system is on cohomology, on the rational cohomology. I have taken, so definitely when I evaluate at a small at a point in U, I will get the value in the 2pth cohomology of that point with rational coefficients. But this does not guarantee that it will be a Hajj class. But if it does remain a Hajj class, I am going to say that the locus of all such points is I will call them the Hajj locus corresponding to gamma. And so here I have given a kind of a set theoretic description, but you can also see this as a vanishing of a certain some holomorphic functions. So this also has a structure of an analytic variety, U gamma. Okay. And then you can also cover this subvariety B with small contractible neighborhoods, and you will get this Hodge locus on this whole of B. So on each of these neighborhoods, you will get this U gamma, and they will all glue together to form this Hodge locus in this big variety. So this gives us the Hodge locus. This is somewhat what I was saying. Topological, this is where the topological obstruction does not exist. This is a bit more stronger than that. In the question I was looking at in the analytic setting, in the infinitesimal setting. Here I am really looking in slightly bigger neighborhoods. Infinitesimal is very, very small, but here I am really allowing much bigger subvarieties. So I am going to go to the tangent space, as Hossein said, that we have to, so these dual numbers are really looking at the tangent space. So this Hodge locus that we have defined, from here, if we want to understand the question in the infinitesimal level, we really have to look at the tangent space to this Hodge locus. Okay.
Ananyo, I think you don't need to consider B gamma, because if this B gamma is global, then it might return back to the same local, I mean, this U, and there must be a kind of radial singularities there. At the end, you just mean you want to say something about U gamma, not this global B gamma.
Yeah. That's right. Yeah, so yeah, it suffices to check for U gamma. Yeah, it suffices to study for a small open neighborhood. We are anyway looking at the tangent space. Right?
Yeah.
Okay, so now let's look at the tangent space to Hodge locus. So there are a lot of different definitions. This is not totally a definition. This is more of a property of the tangent space, but this is simpler to present for a quick presentation. So one way of looking at tangent space to the Hodge locus is that you can look at the cup product. So what were we trying to look at? So what were the objects? On one hand, we were looking at Hodge classes. The Hodge classes were staying in PP. The PP means that it is in the Schiff cohomology of HP omega XP, as is here. Okay. So the Hodge classes lie in here. Now this is slightly more deformation theoretic. This is the space of all first order infinitesimal deformations of X. This parameter, the H1 of Tx, parameterizes all the first order infinitesimal deformations of X. And now if you take this, so the cup product is defined whenever you have a complex manifold, you can always define such a cup product for any sheaf defined on the manifold. So you have a cup product from HP omega XP. So how is the cup product defined, basically? So you first start with the inner multiplication. You have an inner multiplication between omega XP and the tangent space. So if you do the inner multiplication, you see that you will land up in omega XP minus 1, because you are in some sense evaluating one of the so this is a P differential form, differential P form. So you are evaluating, you can write it as sum of product of differential 1 forms. And whenever you can evaluate each of these differential one forms using these tangents, the tangent sections. So you really go, this map comes from the inner multiplication of omega XP tensor with Tx, which gives you a p-1 form. We might be already familiar. And then when you take the cohomology, you can then look at it how it goes in cohomology. You will get the similar, this in the cohomology, it will be additive. You see HP and H1 goes to HP plus 1. Okay. Now, using this, we can define the tangent space, which is you have the natural Kodaira-Spencer map. I do not want to go to the details of the. It comes from a natural, very natural short exact sequence associated to this family that I wrote, the family of smooth projective varieties. So on the left hand side, T0b really parameterizes all the first order infinitesimal deformations in the family. It is corresponding to all the tangent vectors in B. And what does all the tangent vectors in B correspond to? They correspond to all the first order infinitesimal deformations of the special fiber X that are captured in this family, in the family B over B. And this H1Tx is the universal object in some sense, which captures all the first order infinitesimal deformations. And using this, you can define a differential operator going from this tangent space at this point, at this base point that we had chosen of B, going to HP plus 1 omega XP minus 1, given by the cup product, which takes a tangent vector on this base B, going to the cup product of this PP class. Gamma was the PP class. You remember you had HPP. Now you have row of tangent vector coming from the family that lands up in here. So when you take the cup product, you land up in here. Okay, this is exactly the map that you get from this cup product. And the kernel of this map is the, so this is the result that needs to be shown, but this description is very useful. So I am just going to use this description. And the tangent vector to the tangent space to this Hajj locus is simply the kernel of this map. Okay. So the question that we want to ask is, so first of all, we should observe that if we have a first order infinitesimal deformation of the local complete intersection subvariety Z, of course, if you then take the cohomology class of this first order deformation, you will the corresponding cohomology class will give you a Hajj class over these dual numbers. In particular, if you do not have any geometric obstruction, you will also not have any topological obstruction. So if your local complete intersection subvariety deforms, so does the Hajj class, so does the cohomology class of this local complete intersection subvariety. So now we want to ask the other direction. So suppose I know that there is no topological obstruction. So suppose that the cohomology class of Z, suppose that the cohomology class of Z deforms to a Hajj class under this first order infinitesimal deformations. So we want to ask whether this Hajj class, the deformation of this cohomology class of Z, whether this deformation is really coming from the cohomology class of a geometric deformation, in the sense that does there exist a local complete intersection subvariety ZT which is a deformation of Z, such that the cohomology class of this ZT is the same as the deformation of gamma. So I'll make this more precise. So what I was saying is that the one direction why I wrote this question in that way is that so this is a very useful diagram which contains a lot of information. So you start with, say, a local complete intersection subvariety Z in X. then you look at the cohomology class of Z. Okay. You also have the following exact sequence. So the first exact sequence is going to be really surjective on the right if Z is reduced, or if Z is a manifold. Otherwise, you really cannot say that this is surjective, but we do not need it to be surjective. So what you get from these two short exact sequence, the second short exact sequence is the normal bundle of Z in X going to the normal bundle of Z in the bigger. So this is really a projective family. So we always take smooth projective family. This means that the fibers can all be embedded simultaneously into Pn for some n. So you also have the deformation of this subvariety of the special fiber X. So you have Z inside X inside Pn. So you look at NZ normal bundle of Z in X, look at the normal bundle of Z in Pn, then you look at the normal bundle, the co-kernel will be the normal bundle of X in Pn restricted to Z. So these are some standard exact sequence that shows up. So if you're not seeing it, there is no need to worry. I will explain what is the geometry that is coming from these exact sequences. So what we get from is that you have a natural map from this tangent vector, the tangent space at this point O to this irreducible subvariety B. There is a natural map because so this is, so for those who know a little bit of deformation theory, is that because all of this is a smooth projective family, you can fix a Hilbert polynomial. If you fix a Hilbert polynomial, this B will map to a Hilbert scheme. By the universal property of Hilbert scheme, this B will map to a Hilbert scheme. And similarly, the tangent space will also map to the tangent space of that corresponding Hilbert scheme. And we know what is the tangent space to a Hilbert scheme. The tangent space to a Hilbert scheme is exactly given by H0 nx Pn in this setting, because you have X contained in Pn. So the tangent space to the Hilbert scheme is this. So this gives a map from the tangent space of B to the tangent space of the Hilbert scheme. And then there is a natural restriction map. Now you can use this short exact sequence that I showed here, and you look at the boundary map. There is a boundary map going from the H0 of this to the H1 of NZX. Okay, so you have this map. And now this composition is what is known as the geometric, what captures the geometric obstruction, in the sense of this result, that if you take an infinitesimal first order infinitesimal deformation of X corresponding to a tangent vector coming from this family, meaning that T is in T0, T O B in here, then under this map that we have alpha going from this tangent space of B to H1 of NZ mod X, you can see these are quite well defined, because T0B is also a complex vector space. On the right hand side, this is also a Schiff cohomology, which is also a complex vector space. So this is just a map of complex vector spaces. Alpha is just a map of complex vector spaces. So what you can, this nice conclusion that it gives in deformation theory is that the alpha of T is 0 if and only if the subvariety that you started with, that is Z in here, that deforms to a local complete intersection subvariety ZT in here. Okay. So the one thing, so if somebody has not seen this kind of things before, it is always easy to think that Z is contained in XT. So what's the big deal about? So I can take this here. There is an equality, so I can take that, and of course you can write a fiber product, and it is okay. The problem is that if you take ZT as just Z, it is not going to be a local complete intersection. You can see that because it is going to be supported only on the special fiber. So this is just a warning for somebody who has not, who might be thinking that what is the non-triviality in this setup. So so now you can see that the geometric obstruction really is captured by this map alpha. So if Z does not deform to a local complete intersection, this will map to something non-zero in here. So that was the geometric side. Now we are interested in also to compare this with the topological side. What was the topological side? The topological side was when the Hajj class deforms as a Hajj class. In other words, we are looking at the tangent space to the Hajj locus. Now recall the tangent space to the Hajj locus was given by the kernel of this. It was the kernel of this differential map. The kernel of this differential map, you can see, is simply first you apply rho, you come here, and then you apply the cup product. This is exactly the definition that you have here. First you apply the Kodaira-Spencer map, then you take the cup product with the Hajj class. So this map captures the topological obstruction. In particular, if element T in here goes to 0, that means that the Hajj class deforms as a Hajj class. And if it goes to something non-zero, that means that it cannot deform. Now, there is a priori no obvious way to go from here to here. So this is where the semi-regularity map comes in, that there is a map from here to here such that this whole diagram commutes, which means the first thing that you can see from the commutativity of this diagram is that if there is no geometric obstruction, meaning that if you take an element T in here and alpha T is 0, that means that when you go over here as well, it is 0. That means if the geometric obstruction vanishes, so does the topological obstruction. But not the other way around. This map is not necessarily, this map is almost never going to be injective. These are injective for very, very special subvarieties. But you can see that this is a very interesting map. We need to understand this map a bit better, the semi-regularity map. Okay, so I think I'll skip this example. I will come back to this example if I have some time. So what I have, the Bloch semi-regularity map is a bit of a technical object. What you need to see here is that the way it comes up is not too difficult. So if you start with a smooth projective variety of dimension n, and you look at a complete intersection subvariety of codimension p in here, okay? Now you have a natural map from the ideal sheaf. So if you look at the ideal sheaf of z in x, you can always apply the differential operator. You can always take df. If f is defining z, you can always, if f vanishes along z, you can always write df. And you will get a map from this ideal sheaf to omega 1x. So you can also restrict this map to z. And that is what is this d over here. This d looks a bit puzzling, but it is just the restriction of this differential operator. The differential operator you originally define over the ideal sheaf of z in x, going to the omega 1x. And then when you restrict to z, you get this map. And this map you take p minus 1 times. And this is something that is very standard. You get just p minus 1 times of this map. Now you just play around with these two objects. So the homomorphisms from this object to here can be written in several different ways using the adjunction. And what you will finally end up is there is a map from omega x n minus p plus 1 to the canonical, to the dualizing sheaf of Z tensored with the dual of the normal bundle of Z in X. Okay, the reason for doing this is that we are now going to use Grothendieck duality to look at something a bit simpler. So you see, if you take the cohomology, you see you started with this object going from the p minus 1th wedge product to the p minus 1th wedge product here. Okay, that was the hom here, and you ended up over here. And now if you took the n minus, so if you took the n minus p minus 1th cohomology of that homomorphism from the last line, you get this map. And then you use duality, you will get C. Z is of codimension P. That means it is of dimension n minus P. So if you take the dual of this, you will get H1 of NZX. Okay. Similarly, the dual of this is going to be so the dimension of X is n. So then you will get P plus 1, and here you will get Kx tensored with n minus P plus 1. So that means you have to n minus this number becomes is P minus 1. So it's just standard duality. And this map is known as the semi-regularity map. And if this is injective, it is known as a semi-regular subvariety. So it's slightly technical, but you can see that now if you just remember, see what are the objects here. So here there was this H1 NZX, and here there was this object, a P plus 1th cohomology, the sheaf cohomology of omega x P minus 1. Okay, and that is exactly what we wrote here. H1 of NZX to H of P plus 1 omega x P minus 1. And we will probably go through. So yeah, before we go through what happens here, one of the simplest case or more classical case known much before Bloch was this original result in the case of divisors, or more importantly in the case of curves in surfaces. You can look at X, you can take X as a smooth projective surface, and you can look at Z is, you can take any curve inside this smooth projective surface. And so this description, this description of the semi-regularity map is much simpler in this setup, in the sense that this comes as the boundary map of the short exact sequence. And the short exact sequence is this one, which goes from, there is a natural short exact. So how does this short exact sequence comes up? So you can write the short exact sequence from the ideal sheaf of Z in X, going to the structure sheaf of X, going to the structure sheaf of Z. This is like the typical short exact sequence of ideal sheaves that you can have. Now, if you simply just tensor this short exact sequence with OXZ, you will get this short exact sequence. Okay. And if you now look at the long exact sequence associated to this one, you will get a map from H1 of NZX to H2 of OX. And the term before the H1 of NZX is H1 of OXZ. Okay? So this means that if H1 of OXZ vanishes, then Z is semi-regular. But this is very strong. I mean, this is does not always happen. What does happen is that if you take a semi-regular subvariety and you take a high enough, if you twist it high enough number of times, you will end up with something that is semi-regular. So what I mean is that if you up to a twisting by a high enough ample line bundle, you can make a subvariety into something semi-regular by twisting by something which is very ample, sufficiently. Yeah.
Can you just recall what semi-regular mean?
Yeah, exactly. So semi-regular was, we had this semi-regularity map going from this to here. So in this case, so let's do semi-regularity in this case. So what is the map? So the map in this case is H1 of NZX going to H2 of OX. If this map is injective, then Z is called semi-regular. So the boundary map from H1 of NZX to H2 OX, if this is injective, then we say that Z is semi-regular. So one of the ways to check if it is semi-regular is if H1 of OXZ vanishes. So if H1 OXZ vanishes, then the boundary map is going to be injective. And one way you can make this vanish is using the Serre vanishing by twisting it by a sufficiently ample line bundle. Does this make sense?
Yes.
Okay. Any other questions?
Ananyo, maybe just so in this example, you don't need this local component intersection. The definition is general, no? But
Yeah, the point is that for whenever you have a smooth variety, a codimension 1, so this is a divisor. So all wild divisors are Cartier. So whenever you have a smooth projective variety, all the wild divisors are Cartier. So local complete intersection is automatically guaranteed.
Okay.
Good question here. Any other questions? Okay, so kind of a variant of what we were discussing before was that if you start with a smooth projective variety, you can find a smooth projective hypersurface X. So if you start with a smooth projective variety Z, you will be able to find a hypersurface in P2n plus 1 if the dimension of Z was n. Then you can find a smooth projective hypersurface of in P2n plus 1 such that Z is a semi-regular subvariety in X. So what is very important here is that you should note, for example, from this sequence, is that it depends a lot on the embedding. There can be a curve which can be embedded into some smooth projective surface where it is not semi-regular, but in some other smooth projective surface, it is going to be semi-regular. So it very much depends on the embedding. So this is a very important point, that for any smooth projective subvariety of dimension n, you can find a hypersurface in P2n plus 1 such that you can embed it as a semi-regular variety. Now the proof is technical, so I will not go through the proof. Why are we interested in these semi-regular varieties? Is that of the variational Hajj conjecture. So what happens is that if I have a family of smooth projective varieties, I do the same setup as before, that I have a base point, I look at the fiber over the base point, which I call X, and I look at a subvariety in X, and then I look at the cohomology class of that subvariety. Then similarly, I can look at the Hajj locus. We can look at it in a very small setup as well. And then what happens is that if Z was a semi-regular local complete intersection subvariety to begin with, then it satisfies a very strong form of the variational Hajj conjecture, in the sense that the Hajj locus parameterizes all the points in B such that Z actually deforms as a local complete intersection in in the language of obstruction theory, you can say that if you have a semi-regular local complete intersection subvariety, then the topological obstruction and the geometric obstruction are going to be the same. So it will deform as a Hajj class if and only if it deforms as a local complete intersection subvariety. So this is quite a strong formulation of a variational Hajj. So the variational Hajj conjecture just tells you, okay, this is first of all is in an infinitesimal setup. So the variational Hajj conjecture tells you that if you start with the cohomology class of an algebraic variety, and if you deform your smooth ambient smooth projective variety such that this cohomology class deforms as a Hajj class, then after deformation, this new Hajj class is again going to be the cohomology class of an algebraic subvariety. This one tells you even further. If Z that you started with is a semi-regular subvariety, then when you deform your ambient variety, if it remains Hajj, if the cohomology class had remained Hajj, it is going to be the cohomology class of a local complete intersection subvariety, and this local complete intersection subvariety is going to be the deformation of your original local complete intersection subvariety. So this is a very restricted result in some sense as well, because you need that this is semi-regular. Okay, so the last few minutes, I'm going to try to look at this in a slightly different way. We have established that this is an interesting thing to look at. So now we are going to look at it in a more microscopic way. So how do we, let's recall, how do we get this definition of this fundamental class? So the fundamental class that we get is defined using, one way of getting this description is using the check cohomology. We start with a smooth projective variety. We take a local complete intersection subvariety of codimension P. In here, we take an open covering of this smooth projective variety, and in each of these open covering, we have the condition that in this Z is really a complete intersection. In each of these open sets UI, Z is not only a local complete intersection, it's really a complete intersection. Means that there are really P equations that defines Z intersected with UI. So let us call these equations F1i to Fpi. Okay. Now this one is, we want to, so the goal, let's look at the goal. So the goal is to look at an element in this cohomology. We want to end up in the cohomology. So we already have a theory which gives you a topological obstruction theory without this local, without this support. So if you are looking at HP, omega XP, we already know that Hajj class lies in there. So we are trying to translate it into a local cohomology setup. So we want to get the class in this. And this is from the theory of local cohomology, that there is an isomorphism between the higher direct image, P minus 1th direct image of the push forward of omega x, omega p x minus z. So if you remove the subvariety, the local complete intersection subvariety from x, you have an isomorphism between these two objects. So we want to find a class in here. Now this object here you can express in terms of the check cohomology. In terms of check cohomology on each of these UIs, it is something like the h of, sorry. Yeah, on each of these UIs, it is going to be given by this check cocycle. See, if you want to interpret in terms of this higher direct image, you can look at it in terms of the check cocycle. And the check cocycle is given really in this form. where fi, f1 j's are fij's are the equations that are defining this z in this each of these open affine sets. So it's a little bit technical, so do not have to worry about this. There are some more technical things. What I want to stress on is, yeah, let us look at, yeah. So we want to look at the inner multiplication. Let us look at the inner multiplication from the normal bundle of z in X to this local cohomology of omega xp minus 1 with supported in Z. So this is a natural inner multiplication. If you have a sheaf homomorphism going from, so an element in here is by definition going to be a sheaf homomorphism. It's a module homomorphism from this ideal sheaf of Z in ui restricted to itself, going to the structure sheaf, and you simply evaluate it at each of the equations in an alternating fashion, and then you divide it by this object because we want it to, you want it to be in this class. So that is slightly the reason you don't have to worry too much, but this is roughly the formula that you take the homomorphism and you evaluate. So you see that this is somewhat like taking the cup product. So what we were doing, the cup product in the beginning is kind of close to this. And the point is that this is indeed quite close, which as shown by Bloch, is that the original, what was the original semi-regularity map? The original semi-regularity map was going from the H1 of the normal bundle to HP plus 1 of omega xp minus 1. Okay. Now, using this, you can even, it factors through, the same semi-regularity map factors through. If you look at the H1, so you have this inner multiplication going from in the normal bundle of Z in X to this local sheaf cohomology. So if you are not used to this local sheaf cohomology, you do not need to worry. So the only way, the easy way of thinking about it is that cohomology somewhat looks at the, you take an injective resolution, then you take the global sections, and then you take the cohomology. Here, instead of taking the global section, you do the same, but instead of taking global section, you look at the global section which are supported at this subvariety, and that will give you this description. There are some much simpler descriptions as well using check cohomology, but using open coverings. But as we really saw before, there are simpler descriptions, but I do not think I have the time to go through that. So what is important is that this, we, instead of studying this classical semi-regularity map, we can instead look at the other map, which is which it factors through. Now, the surprising thing is that there is quite a bit of geometric information that is hidden in this map, and at least we had we worked it out in the case of divisors, and we expect that it should hold in higher codimensions as well. What happens is that it is possible that if you take an element in this tangent vector, suppose that when you go here under, you remember that there was a map alpha t going from T0b to H1nzx, which captured the geometric obstruction. If alpha t was 0, that means there is that means Z deforms as a local complete intersection subvariety. So suppose that there is a t such that it over here, when you came here, it is still non-zero, but when you ended up in here, it is 0. Suppose that there is such a t. When can such a thing happen? This will happen if Z does not deform as a local complete intersection subvariety, but a multiple of Z can deform as a local complete intersection subvariety. So this was something very interesting that can happen, which we do not see from the original semi-regularity map. that there is an obstruction to the deformation of Z. This typically happens that if you have a multiple of a subvariety and it deforms to something which is slightly less, slightly more reduced, but the underlying topological space does not deform. So this happens in similar situations. For example, if you have two lines which deforms to a conic, but the line itself does not deform, this will give rise to similar properties, that here it will be non-zero, but here it will be zero. So this was something very interesting that is given by this theorem that that I just said, and I'm already out of time, which I will just quickly say is that instead of the semi-regularity, we try to replace it by this map. So this is because this will then, for example, in the surface case, this will be this is a proper subvariety of the effective divisor. In particular, if D was a curve, T will be points. So you have a natural map from this is a natural restriction map from the structure shift of OX minus T to OX minus D. This is a much smaller, this one is a much smaller subvariety. So there is a natural restriction map here. And this local cohomology theory gives you a map in this direction. So if you look at this composition of this map, this contains quite a bit of information. In particular, this tells you that if you look at the co-kernel, so if you look at the, so you have this map, you're right. If you, the co-kernel of this map from H1OXT to H2DOX, the co-kernel of this map is going to contain all the information of the topological obstruction. So previously we knew a bit less about the topological obstruction, but this tells you that if the cohomology class deforms as a Hajj class, if and only if the image of this goes to 0. And in terms of semi-regular, it translates similar to the original semi-regularity, which says that it is semi-regular if and only if it is T semi-regular with respect to all proper subvarieties. So I stop here. Thank you.
Yes, thank Ananyo. Questions?
Ananyo, so
Yeah.
do you have control of this n, the number n? I mean, or
which number n?
I mean, the multiple of this in your your first theorem with the biswas that you showed. There is a multiple.
Let me share. Hang on.
I remember that with your result in with in there, you told me that you don't have control of the degree of the hypersurface.
Right, right.
But how about this n, this multiple? Do you?
Right. That's this n. Right. No. The point is that this n is we do not know. No, we do not. It does not need to be large enough. But we do not know much about when it starts to happen.
Which result you use that this n appears? I mean.
So this is very different from with Inder. This is very different. This is really using just this analysis of these equations. So if you use these equations and apply this inner multiplication, there you will get that. So this n appears from there. The proof is very technical, so it is just using this studying this map. It is really just studying this map. You have to compare this map with a multiple of this map. So this one is with Z. You can replace it with NZ, and then you have to show that if it is 0 in here, that means that there will be an NZ where it will be 0 in here. So there will be a commutative diagram which has Z comparing with NZ. Does this make sense?
Okay.
Perhaps we can stop recording. Ask more wild questions.